Have you ever wondered how a really big, powerful motor knows the exact perfect moment to kick into high gear? Well, we're about to uncover a brilliant little physics trick that's hiding inside this simple black box. Okay, so let's just dive right into this because it's a really fascinating problem. See, if a motor disconnects its starter circuit too early, well, it just stalls out. But if it does it too late, it will literally burn itself to a crisp. So how does it nail the timing perfectly every single time without using any kind of clock? So first, we got to understand the basic challenge here. We're talking about large single-phase motors, like the kind in a big air conditioner. And they have a major case of inertia. They need a really big push to get going. To get that massive initial push, they use something called a start capacitor. And you can just think of it as an electrical shot of espresso. It gives this powerful jolt of energy to get that heavy rotor spinning. But that jolt is way too intense for continuous use. If you left it connected, you would absolutely destroy the motor's sensitive wiring. So what you need is a switch, but a simple timer isn't going to cut it. The time a motor needs to get up to speed can change all the time, depending on how much load it's under. No, we need something smarter, something that can actually sense the perfect moment to act. So what did engineers come up with? They came up with this pretty humble-looking component called a potential relay. I mean, on the outside, it's really just a plastic box with a couple of terminals. But don't let that fool you. This thing isn't measuring time, it's listening. It's listening for a hidden electrical signal that's coming from the motor itself. It's a voltage-sensitive switch. To really get how this works, we've got to look inside. As the instructor in our source material says, the absolute best way to learn is to take things apart. So let's do that. Okay, once you pop it open, there are really three key parts. You got the casing, of course. Then you've got the heart of the whole device, a coil made of thousands and thousands of turns of hair-thin copper wire. And finally, there's a little mechanical plunger that's connected to a set of electrical contacts. Now here's the crucial part. Those contacts are normally closed. That just means that, by default, electricity is flowing right through them. So how does this pretty simple device know when to activate? Well, the secret is in a force that the motor creates all by itself as it gets up to speed. And this brings us to this really cool concept called back EMF. So here's the thing. Any motor that's spinning is also at the same time a generator. As it spins, it's creating its very own voltage that literally pushes back against the power that's running it. And the faster that motor spins, the higher that back voltage gets. This back EMF is definitely the key, but it's not quite strong enough on its own to actually trip the relay. So the system needs a way to amplify this voltage, to crank it up to a much higher level. And the way it does this it's absolutely ingenious. Right, and this is where we find the absolute cleverest part of this whole design. The motor uses its own parts to basically do a completely different job in disguise. So inside the motor, you've got two main coils of wire, the run winding and the start winding. As that rotor starts spinning, it induces that back EMF we just talked about into both of those windings. But here's the trick. Those two windings, they are not identical. See, the start winding is wound with many, many more turns of wire than the run winding. And because of that, it acts just like a step-up transformer. The run winding becomes the primary coil, and the start winding becomes the secondary. The motor literally becomes its own power booster. This quote from the source material is just the perfect way to think about it. The exact same physical principle, induction, that makes a transformer work is what's generating the signal voltage inside the motor. And the effect is pretty dramatic. I mean, even if you're only putting, say, 120 volts into the motor, this internal transformer effect can cause the voltage across that start winding to spike way up to 180, 190 volts, maybe even higher as it reaches full speed. So, this huge voltage spike, that's the signal. It is the precise trigger that potential relay has been patiently waiting for. Remember that coil of really thin wire inside the relay? Well, it's wired directly to the start winding. It's basically acting like a tiny voltmeter, just constantly sensing this rapidly increasing voltage. Now, that relay is very precisely engineered to react at one specific voltage, and we call that the pickup voltage. The moment the start winding's voltage hits that target number, the coil's magnetic field gets strong enough to physically pull the plunger and open the switch. And there's also a dropout voltage, which is just the lower point where the magnet gets weaker and lets the switch close again. So here's the entire elegant sequence all in one go. The motor starts, the rotor spins, and it generates back EMF. The voltage gets stepped up in the start winding. Once that voltage hits the pickup level, click, the relay coil becomes an electromagnet. It yanks the switch open, and that disconnects the start capacitor, taking it safely out of the circuit, all at the perfect moment, determined entirely by the motor's own speed. Really, the big takeaway here is just the sheer elegance of this design. There are no microchips, there are no timers. The motor is creating its own feedback loop, just using the basic laws of physics, electromagnetism, and induction to regulate itself perfectly. It's really an incredible example of self-regulation, all hidden away inside a simple little black box. And it makes you wonder, doesn't it? What other dumb components are all around us, just hiding a brilliantly simple physics trick, doing their job perfectly, right under our noses?